On the morning of June 30th, 1908, the sky over a remote expanse of the Siberian taiga violently tore itself apart. A blinding light, rivaling the intensity of the sun, streaked across the horizon, followed by a concussive shockwave of unimaginable power. Trees were instantly stripped of their branches and snapped like matchsticks. A deafening roar echoed across the desolate landscape, a sound so profound it shattered windows and knocked people off their feet hundreds of miles away. We are drawn into the heart of the Tunguska Event, a cataclysm that unleashed the energy of roughly 1,000 Hiroshima bombs, yet left behind a puzzle that would confound scientists for over a century. The sheer scale of the devastation was almost beyond human comprehension. Across an area spanning 2,000 square kilometers, an estimated 80 million trees were flattened, radiating outward in a massive butterfly pattern from a central epicenter. Entire herds of reindeer were incinerated, and the very earth seemed to have been scorched by an otherworldly fire. Yet, in the immediate aftermath, the world remained largely ignorant of the disaster. The extreme isolation of the Podkamennaya Tunguska River basin, coupled with the political upheaval brewing within the Russian Empire, meant that this colossal release of energy occurred in near total obscurity, witnessed only by the indigenous Evenki people and a handful of distant settlers. Historical records indicate that those who survived the periphery of the blast experienced something akin to the apocalypse. Trading posts reported a column of fire piercing the heavens, followed by a thermal pulse so intense that witnesses believed their clothing would spontaneously combust. Seismic stations across Eurasia registered massive tremors, and barographs in the United Kingdom recorded fluctuations in atmospheric pressure that circled the globe twice. For nights afterward, the skies over Europe and Asia glowed with a strange silvery luminescence, bright enough to read a newspaper by at midnight. The atmosphere itself had been profoundly disturbed, heavily seeded with microscopic dust that refracted the high-altitude sunlight. Despite the global atmospheric anomalies, a formal scientific investigation into the mystery would not commence for nearly 2 decades. It was not until 1927 that Russian mineralogist Leonid Kulik, driven by reports of a colossal meteorite strike and the promise of valuable iron deposits, led the first expedition into the unforgiving wilderness. Kulik and his team endured brutal conditions, navigating treacherous swamps and dense, mosquito-infested forests to reach the heart of the destruction. They expected to find a landscape dominated by a massive impact crater, a gaping wound in the earth surrounded by the scattered remnants of a cosmic visitor. What the expedition actually discovered defied all scientific expectations of the era. As Kulik reached the calculated epicenter, the anticipated massive impact site was entirely absent. Instead, he found a haunting forest of telegraph poles, standing dead trees that had been stripped of their bark and branches by the sheer vertical force of the explosion, yet remained perfectly upright. Surrounding this eerie central zone, the flattened timber lay pointing precisely away from the locus of the blast. The ground was scarred by shallow bogs and permafrost deformations, but there was no definitive chasm, no massive displacement of rock, and most bafflingly, not a single fragment of meteoric iron. The missing crater presented an unprecedented scientific paradox. If a physical object large enough to level 2,000 square kilometers of forest had struck the Earth, the resulting excavation should have been monumental. Kulik spent years draining bogs and drilling into the frozen soil, desperately searching for the elusive payload, but the Earth yielded nothing. This glaring absence of primary evidence transformed a simple meteorite strike into a profound anomaly. The data forced researchers to question the very mechanics of cosmic impacts, suggesting that the destruction was caused by a mechanism entirely foreign to early 20th century geology and astronomy. In the vacuum of physical evidence, a myriad of unconventional hypotheses began to flourish. For decades, the intellectual landscape surrounding the Siberian mystery was populated by increasingly exotic theories. Some researchers proposed that a miniature black hole had passed straight through the Earth, while others suggested the annihilation of a chunk of antimatter entering the upper atmosphere. In the mid-20th century, The idea of an exploding alien spacecraft even gained traction among certain fringes, fueled by the seemingly unnatural mechanics of the blast. While these ideas lacked empirical support, they perfectly illustrated the desperation of the scientific community to explain a phenomenon that simply did not fit the established paradigms. The turning point in understanding required a fundamental shift in how scientists visualized the collision. The persistent focus on a ground-level event was fundamentally flawed, contradicted by the upright trees at the epicenter and the vast, shallow spread of the damage. Researchers began to analyze the specific butterfly-shaped footprint of the fallen forest, realizing that the energy distribution matched the physics of a detonation that occurred high above the ground. The physical evidence was not missing. It had been vaporized. The object had never reached the surface, entirely altering the parameters of the investigation. Modern scientific consensus now confidently attributes the devastation to an airburst explosion. We understand that a massive kinetic body, either a stony asteroid or a fragment of a comet, entered the Earth's atmosphere at a staggering velocity of roughly 54,000 kilometers per hour. As this object plunged into the increasingly dense layers of the lower atmosphere, the aerodynamic pressure and intense frictional heating overwhelmed its structural integrity. At an altitude of approximately 8 to 10 kilometers above the surface, the object catastrophically fragmented. This sudden disintegration released its immense kinetic energy in a fraction of a second, creating a devastating shockwave that propagated downward, flattening the forest below without excavating a crater. Sophisticated computer modeling has allowed researchers to reconstruct the mechanics of this catastrophic airburst with remarkable precision. By simulating the atmospheric entry of various celestial bodies, scientists estimate that the Tunguska object was relatively small, likely measuring between 50 and 80 meters in diameter. Despite its modest size, the sheer speed of its descent translated into an explosive yield estimated between 10 and 15 megatons of TNT. The models perfectly replicate the thermal radiation that scorched the epicenter and the downward-directed blast wave that created the haunting telegraph poles, finally aligning the theoretical physics with the physical aftermath observed by Kulik decades earlier. While the airburst mechanism is universally accepted, the precise composition of the cosmic intruder remains a subject of rigorous debate. For years, the prevailing theory favored a comet, composed largely of volatile ice and dust, which would easily vaporize upon atmospheric entry, neatly explaining the lack of macroscopic debris. However, recent aerodynamic simulations challenge this assumption. A fragile comet would likely disintegrate far too high in the atmosphere to cause the specific pattern of ground damage seen in Siberia. Consequently, many astrophysicists now argue for a dense, stony asteroid, which could penetrate deeper into the troposphere before the catastrophic pressure differential triggered the explosion. The search for the perpetrator eventually shifted from massive iron boulders to microscopic traces hidden within the landscape. Expeditions in the late 20th and early 21st centuries began analyzing tree resin and peat deposits dating back to 1908. Deep within these biological archives, researchers discovered microscopic spherules of melted rock, enriched with high concentrations of iridium, nickel, and other elements highly indicative of an extraterrestrial origin. These tiny metallic droplets are the vaporized ghost of the asteroid, condensing in the atmosphere after the explosion and raining down upon the devastated forest. The evidence was there all along, merely scattered on a microscopic scale. The resolution of this century-old puzzle fundamentally alters our perception of the cosmos and our place within it. The Tunguska anomaly demonstrated with terrifying clarity that Earth does not need to be struck by a civilization-ending behemoth to suffer catastrophic damage. A relatively small asteroid, entirely undetectable by the astronomical technology of the early 20th century, possesses the capacity to obliterate a modern metropolitan area in an instant. The realization that such immense destructive potential can manifest entirely as an atmospheric shockwave, leaving no crater as a warning, forced a profound reevaluation of the celestial threats lurking in our solar system. This vulnerability was starkly reinforced over a century later. In 2013, the skies over Chelyabinsk, Russia, were shattered by another, albeit smaller, airburst. A 20-meter asteroid detonated in the stratosphere, producing a flash brighter than the sun and a shockwave that injured over 1,000 people. The Chelyabinsk meteor served as a visceral, modern-day validation of the Tunguska models. It provided scientists with unprecedented observational data, captured on countless dashboard cameras, confirming the violent mechanics of atmospheric entry and fragmentation. The echoes of 1908 had returned, transforming a historical curiosity into an urgent contemporary reality. Today, the legacy of that remote Siberian explosion is the driving force behind modern planetary defense initiatives. Space agencies worldwide now actively map the trajectories of near-Earth objects, recognizing that the threat of a small, city-killer asteroid is not a matter of if, but when. The investigation into the 1908 cataclysm evolved from a bewildering trek through a shattered forest into a sophisticated global endeavor to safeguard our world. By deciphering the violent language of the airburst, we have transformed a devastating cosmic ambush into a catalyst for our own survival, looking upward not just with wonder, but with a vigilant, protective gaze.